We talk a lot about how bad red dwarf stars are, how dangerous the flares are that they can release to any planets that might be in orbit around them. Of course, as we're looking for more and more exoplanets, wondering if there could be life on these other worlds, you've got to take into account just what a dangerous environment it would be to live next to one of these red dwarf stars. Do they settle down over time? And how difficult is it to observe them and try to figure out what's planet, what's flare, what's star? It's a challenging problem. So my guest today is Dr. Ward Howard from the University of Colorado, Boulder. And he has been looking into the kinds of flares that these red dwarf stars are producing, and can you untangle that flare from just the observations of the star. And you can see this is very important while you're trying to observe, say, the atmosphere of the planet that's passing in front of the star at the same time that the star is having a flare. And, you know, can you get good data from this? And so we talk about what kind of influences these might have on some of the observations that have been made so far and what can be done about it. But then we just talk about red dwarf stars and habitability in general. How dangerous is it? What kind of impact does it have on the planets? And are there any ways that planets could survive being that close to such dangerous stars? So enjoy this conversation with Dr. Ward Howard. How dangerous and severe are the flares coming off of red dwarf stars?
They're extremely large. In fact, we think that they're the dominant source of the high energy radiation experienced by planets around red dwarfs. The amount of radiation can increase by multiple orders of magnitude in the X-ray and in the UV. And even in the optical, the very nearest star to our sun is a star called Proxima Centauri. And in 2016, a survey that I was involved with observed a flare from the star where the star got brighter by a factor of about 70 times in the wavelengths of light that you and I could see over the span of about 4 minutes. So I had led a paper on that, looking to see like what effect that might have on an atmosphere. And, if repeated events of that type continue to happen in Earth-like atmosphere, I would see its ozone levels depleted in maybe 100,000 years. So, and then that would lead to germicidal levels of, UVC radiation on the surface, even for, microorganisms that are resistant to radiation, so extremophile organisms. So the possible implications for the existence of life are severe, but there's also a lot we don't know. One example of that is, on Earth, we think that UV radiation was necessary for the prebiotic chemistry that led to the existence of RNA and ultimately DNA, but there's not a sufficient source of that UV light to power that prebiotic chemistry on planets around red dwarf stars. And so flares might actually be necessary for the existence of life on those sorts of systems too. So you could think about maybe a flare Goldilocks zone of just enough flare radiation to power life, but not so much as to permanently end it.
I want to sort of understand the scale of these flares because I think there's like two variables going on here. You've got the size and mass of the star. So like a red dwarf star, which could have 7.5% the mass of the sun compared to a main sequence star like the sun, or even much larger stars than the sun. And then compare that to the sort of the total amount of energy that is released by the flare. So if you took like a very flary red dwarf star and just compared the amount of energy that is being released to, say, a big flare that the sun will produce, is that star producing more just raw energy compared, or is it like proportional?
It is proportional, but during these so we call the largest stellar flares, which are just solar flares from other stars, we call these super flares. And these are flares that are at least a factor of 10 larger than the largest flares that we've ever seen from our sun. The particular flare I was just mentioning would have been about a factor of maybe 20 larger than that. And we see some flares, super flares from other stars that really reach factors of 10,000 times greater than their host star. So with the example of even the Proxima flare, Proxima is normally invisible to the naked eye. It's just too faint to see. And the star, if you look at the images during the flare, the entire stellar emission is essentially the flare, to the point that in the research community, we often ignore the host star when we're analyzing the red dwarf flare spectrum, right, because it's so weak that it's like a factor of 5 or 10% very often compared to the emission from the flare itself.
And so if you transplanted one of those flares from, say, Proxima Centauri onto the sun, it would just be still on its own a dramatically brighter flare than anything the sun is known to produce.
In the current era, yes. There's some evidence that the sun emits something like that about maybe once every 1,000 years or so. And I would refer you to a study by my friend and colleague Yuta Natsu on that. But yes, it would be a significant enough event till we would not have this conversation right now, because the entire electrical grid would be down and the entire atmosphere would be magnetically ionized.
Right. And then this is compounded in theory by the habitability of these planets, because if you want to have a habitable zone around a red dwarf, you got to be tight, got to be close up.
Yeah, so an X1 class flare from the sun, which is measured by the GOES satellites in Earth orbit, would say a flux of 10 to the minus 3 would be an X class event, 10 to the minus 3 watts per meter squared. And then if you take Earth and move it to the distance of these red dwarf habitable zone planets, suddenly that's about 400 times more radiation from the same size flare. So now you'd be talking about a Carrington event level event, every time one of these hits your planet, rather than just every few hundred years.
Every day. So, I mean, I think we're going to circle back around and talk about sort of the implications of habitability and what possibilities might be. But I want to talk about your research specifically, because you propose that these flares are confounding our exoplanet observations a little bit, making it a little more difficult.
Absolutely. So the size of so transmission spectroscopy is an extremely difficult measurement to make for many, many reasons. And the first is the size of the signals that we would want to observe in the near infrared are, really on the order of, 50 parts per million or 100 parts per million. And you really want to have better precision than that. You would like your instrument to be more in the 20 parts per million range to be able to better resolve even the smaller features. And so this is why the only planets that we can even look for things, secondary atmospheres, say like a carbon dioxide atmosphere or a water atmosphere for an Earth-sized rocky planet, is if the host star is an M-dwarf, because the stellar radiation makes it harder to observe those very, very small signals. So for example, if this planet were orbiting a sun, a star like our sun, which is a G-dwarf, it would be impossible with current technology, including JWST. But it is possible when the star, as you said, is 7% the mass of the sun. It's so small that the relative signal of the planet is much, much larger. So that's the first thing that makes it challenging. And then the second thing is something called the transit light source effect. Have you heard of that before?
No.
So this is what happens. So the way that transmission spectroscopy works is you have to see what changed. You take the spectrum of the star before the planet passes in front of it, and then you compare to the spectrum of the star when the planet is in front of it, and you subtract those two to isolate what changed, which should be the planet. I think you can see the problem with that pretty immediately, and that's called the transit light source effect, which is that the star can also change.
Right.
So this is essentially any time that the spectrum of the disk integrated spectrum of the star, because we obviously can't resolve a stellar disk, so we have to integrate all of that light before the transit of the planet in front of the star. And anytime that spectrum differs in any way from the spectrum of the star while the planet is in front of it, it's going to lead to contamination. And that can be due to occulted spots or spot crossings, where you'll see a little bump in the transit as the planet occults a star spot on the star. Another thing that could cause this will be unocculted star spots. So, for example, there are a lot of questions about have we even detected, say, water vapor in certain exoplanet atmospheres, or is this just water vapor from the unocculted star spots that's varying in the transmission spectrum? So, there are questions about that. So unocculted spots, because those still change the properties of the disk integrated spectrum of the star versus the spectrum of the transit chord. And the transit chord is the path that the planet takes across the star. So that's another source. And then, of course, flares, time variable sources of emission, also add to contamination. And that's one that hasn't received as much attention until now because it's time variable. And so people often think about these persistent sources like spots and trying to correct for those. But less attention has been given, I think, to the flares until people started pointing their JWST telescope programs at these active M-dwarf stars and were in for a bit of a shock. Right.
Watching, say, an X-class flare as they were hoping to see their transit. and then kind of
Yes.
wondering, is this a bigger problem than we thought? So I guess, how big of a problem do you think it is?
Well, I don't know if you're a Star Wars fan or not, but I'll take you back to the prequel trilogy because everyone thinks that Anakin Skywalker is going to be the hero of the Jedi. And Anakin Skywalker has a big reputation to live up to. And then ultimately he betrays the order and, is not what everyone had hoped for. And then Obi-Wan Kenobi, says, you were the chosen one. You were supposed to be this, paragon of ability and virtue. And I think that same thing is to some degree true of these M-dwarf planet host stars because of the flares. Due to their signal to noise properties, they have the highest transmission spectroscopy metrics, or the ability to actually see these planetary atmospheres of any nearby stars. And the key one of those is TRAPPIST-1 because it has 7 planets that are about the size of the Earth. 3 of those are in the habitable zone. It's kind of an ideal system, but then about half of the transits are affected by these flares that make it extremely difficult to pull out the transmission spectrum of the planets. And you need multiple transits to build up the signal to noise to make all of these amazing detections, even including the possibility of biosignature detections. That requires a lot of transits. And if half of those transits are affected by flares and you have to throw those out, suddenly the star might not seem quite so much like the chosen one anymore. So I often actually throw that meme up of Obi-Wan when I'm showing this in professional talks.
Well, and we've all been waiting for that spectroscopy results from the TRAPPIST-1 system, and we've got 2 so far, and it's been a year. And so, I mean, I don't know if you can actually, if you're on the team that's studying it, but what I'm hearing is that the variability of the star, the potential flares, is making it difficult to get the kinds of observations that give them the confidence that they would like to be able to publish.
Yes, we have I was not on the papers that actually published the atmospheres. I am on the larger team, but so some of those papers use other methods. The one that I was more involved with is something called the NEAT collaboration, which is PI'd by Olivia Lim, who it's amazing that she's actually done all of this. She's a graduate student who's managed to lead a first cycle JWST program, publish the first transmission spectrum of TRAPPIST-1b. I'm just blown away. It's amazing. But that's the effort that I've been more involved with. And we have second iterations of reductions where we do account for the flares. But in the initial reduction in the paper she just published in AppJ Letters a couple of weeks ago, we did not observe any evidence of a secondary atmosphere around TRAPPIST-1b. And that's also expected as you go back to the habitability implications. This is the closest planet to the star. It's the most impacted by photochemical escape. So it's quite likely to be without an atmosphere. The first planet where we're likely to see an atmosphere is TRAPPIST-1d. So those observations are currently being reduced, as we speak. And there are flares during those transits. So, I think we'll have to see how it goes. But TRAPPIST-1g, TRAPPIST-1d, those are the ones where there's more hope that we'll actually be able to detect a secondary atmosphere at this point.
But that would help explain the delay. As you said, back to the Anakin problem, it was supposed to be the chosen one. And in fact, the star is making it tough to get the observations that you require. And at the same time, I'm sure there's just this growing horror at what those poor planets must be experiencing.
Yes. Both of those are true. So part of what takes so long is you have to use multiple pipelines, not just for this science, but JWST is new. So right now there aren't accepted practices. So, for any atmosphere you want to publish, you want to run it through several independent pipelines and see if the same features persist. This is one of the things that's really concerning about the claimed dimethyl sulfide from K218b, which orbits another M-dwarf planet, or another M-dwarf star rather. In that case, they only used one pipeline, and we want to know across multiple pipelines is something persistent. So that takes time. And then there's different ways of handling the stellar activity, the spots, the plages, the flares, the faculae. So you might do a joint fit, but then the flares are so big that they might actually swamp the signal of the planet. So you also want to try other types of fits by just treating the contamination from the star and then just looking at the planet and seeing, between these different approaches what changed. And that's the approach that Olivia Lim took in her paper, which I think is probably the right way to go. And it takes a lot of time.
Right. And I think that was like a 1.6 sigma. I forget. The signal is fairly low on the dimethyl sulfide detection. Yes. And what I'm hearing is that if you consider these other possible sources of contamination in the image, don't be surprised if the sigmas continue to drop on that detection.
Well, other pipelines may show no features there. The problem is that the data in the paper hasn't been made available. The underlying data, the raw data, has not been made available yet to be run through other pipelines. So once that happens, I think will really tell us, how robust that particular feature is. And I wouldn't be surprised if what you're saying is true.
I mean, I always go back to the controversy that's already happening about the discovery of phosphine at Venus. And Venus is right there. Right? It's like right next door. We could not, unless we had a spacecraft like literally in the atmosphere, we could not be more capable of examining the atmosphere of that exoplanet analog. And yet people argue. And so I'm preparing myself for the future arguments about all of these exoplanet discoveries. And so I maintain a very skeptical approach to all of it. So what's the solution? And so you propose a way that we can account for these flares on the stars.
Yes. So this particular paper is just looking at removing the flare radiation rather than, say, the spots of the faculae. I have ideas about how to remove those too, but that's a separate topic. That's what I'm excited about now, is trying to find a way of fully characterizing the stellar emission. But with the flares,
that'll be my last question. Then we'll get there in a second. But
we'll get there.
Yeah.
But coming back to just the flares, the thing that up until now, no one had ever actually observed flares in this particular wavelength range. And so this is the wavelength range where you're wanting to observe the planet atmosphere. If you haven't actually seen any flares at that wavelength range, then you don't know how to characterize them and you don't know how to correct for them. I was actually very pleasantly surprised at how well the flare emission behaved as a function of wavelength. I was assuming we were going to need something called non-LTE or non-local thermodynamic equilibrium, fully physics forward models to try to capture this emission and correct for it. And we did run some of those models in the paper. I was assuming it was going to take that, and we were able to use a simple Planck function to fit and remove the flare continuum when we saw it. The spectrum was so beautiful. I started with the spectrum of the star, and then I looked at times in the spectrum where there was no flare, and then times where there were flares, and then used that to essentially subtract off the quiet star to see what was left, what changed. And the spectrum of the flare just popped out as this beautiful, black body curve with an effective temperature of around 5,000 Kelvin, which is also lower temperature than people often assume for flares, and that can lead to some other issues. But it's actually very consistent with some solar flare and stellar flare work that's been carried out by Adam Kowalski at the National Solar Observatory and here at CU Boulder as well, who finds multiple temperature components in these events. So it did actually follow some theoretical predictions, which is good. But I was impressed with how well it worked. I was not expecting it to work that well.
And so, based on what you were able to do post-processing, do you think that there's a path to have this be sort of part of the standard pipeline for JWST and maybe the upcoming Ariel? A lot of future atmospheric analysis work is going to be done. Do you think there's a pathway to do this?
That's exactly why I released the paper when I did. The JWST Cycle 3 program deadline is October the 25th. I and many, many colleagues are frantically writing our proposals as we speak. And that's exactly why I released the paper, because I think this sort of technique is exactly what we're going to want to do to handle these sorts of flares. And this is not the only system that flares. TRAPPIST-1 is not a one-hit wonder in terms of its flares. There are many JWST programs observing other systems like LTT 1445A, which is a flare star, L9858, don't quote me on the exact string of numbers, which has 3 planets that are rocky that have had multiple JWST programs observe them. Stars like AUMIC are favored targets for observation, so those will probably be observed. So this is absolutely a technique that I think will have to be a standard part of our repertoire for correcting these events. And even so, this is only the first step. We only got 80% correction using this particular simple technique. We can do better than that. And so I think that, as we continue to get a bigger sample of flares, we'll be able to better understand what the physics is that's driving the emission in these wavelength ranges. Like on the sun, we see this thing called backwarming, where overlying flare loops, so flares have loop-like structures. You may have seen these pictures of solar flares before. And that energy from the loop can then propagate down into the star and then give secondary heating at lower levels in the star. And so that's called backwarming. And we suspect that that may be at play and is maybe one of the reasons why our physics-based models didn't quite capture that spectrum of the flare, whereas the simple black body fit actually did so well. And as we continue to improve these physics-based models, I think eventually we may be able to get something like maybe a 95% improvement rather than, say, just an 80% improvement.
And so some future exoplanetary researcher, as they're choosing the wavelengths they want, they're choosing the filters, they could also say, and while you're at it, please gather this additional spectra so that I could subtract any possible flares that happen during it. Like I don't know, I'm thinking like if you do some astrophotography, like you take like a blank first and just get a background and like, here's how flaresy this star is. And then you can then run that through and subtract it for all your future observations. That's really exciting. I mean, I love that, we get this new telescope, we learn the terrible truth, and then someone like you comes along and goes, here's a software fix, right? There you go. Problem solved, partly. So yeah. So I'd like to shift gears down and just talk about these stars in general. And, because right now they are the low-hanging fruit. They're not the ideal stars that we want to be looking at for potentially other Earths, but this is what we got thanks to Kepler and other observatories. So what do we think is the sort of the life cycle of these red dwarfs and their flares? Like, from when they form to when they stop being so dangerous? What's the sort of like the scale on this?
So I'll add one more piece to that, which is how do the planets evolve with the M dwarf or red dwarf stars? Because they actually co-evolve. So, and I wanted to mention that because you mentioned Venus, and it turns out that Venus is probably a much better analog to rocky planets around M dwarf flare stars than is the Earth and its atmosphere. And the reason goes back to the question you just asked about how did the flares evolve over time? So in the very earliest stages of what's called the pre-main sequence, when these stars are still very, very young and they still have protoplanetary or debris disks. So we're talking ages of, 10 to 30 million years. These are very, very young systems. At that stage, the flares are very extreme and very regular. And then as the star ages, it spins more and more slowly as it's depositing angular momentum into its disk and into its own, stellar wind. And so old stars, old M dwarfs, spin more slowly than do young stars. M dwarfs in particular, or red dwarfs, spin down or age extremely slowly compared to stars like our sun. So that effectively means that the youth of a red dwarf star is so long that its period of extreme flare emission is much, much, much longer than for a planet like Earth orbiting a star like the sun, which means that amount of high energy X-ray and UV radiation for a planet orbiting a red dwarf star in its youth is going to have a outsized impact on the evolution of the planet alongside the evolution of the star as compared to a planet like the Earth. And so this means that we cannot expect an Earth-like atmosphere for a planet orbiting a red dwarf star. I think if we want to look for Earth-like atmospheres, we're going to have to look at stars like G-dwarfs, and that's going to require future observatories. But if we think specifically about red dwarf stars, what we could expect to see is something called a steam atmosphere. And this is where you essentially get a runaway greenhouse effect due to all of that extra X-ray and UV emission during the youth of the red dwarf star when it's emitting far more flares than it would at a later age. And that could potentially be detectable through H2O features. These atmospheres also probably still have a high amount of carbon dioxide, so there's a chance to look for those sorts of features. So I think Venus or exovenuses are actually the way to think about what we might detect. So I just found it very prescient that you mentioned Venus and the possible phosphine result.
And so, I mean, the one possibility is that you get the formation close to the red dwarf. The other possibility is you get a migration from farther out. But, I mean, are we talking billions of years of severe flare activity or hundreds of millions of years? Like how long is a planet going to be in the danger zone?
It looks like around 200 to 300 million years.
Right.
It looks like these stars, the red dwarf stars, age or begin to slow down at around 700 million years. And by a gigayear, they've sort of reached some form of maturity. Although it's important to remember that, even then, they're still far more flare active. For example, TRAPPIST-1, we think, is many billions of years old, as is Proxima Centauri, which hosts Proxima Cen-b, which is the nearest potentially, habitable zone exoplanet that's rocky. So, all of these, are still very, very flare active. And even inactive red dwarfs like Barnard's star that have planets like Barnard B, there have been models that have shown that it's quite likely to, have lost oceans worth of water even in its, older age due to this flare activity. It's just decreased relative to what it was at, say, 40 million years old versus 10 billion years old, as in the case of Barnard B.
So we might have to wait billions of years. Like it hasn't happened yet in the age of the universe. Like they're going to last for potentially trillions of years, but they still haven't settled down to the point that you would want to live there.
The problem with that is that your atmosphere for your exoplanet has to come from somewhere. So the atmosphere a planet is born with is called a primordial atmosphere, which is mostly hydrogen-helium dominated. A great example of such an atmosphere would be the planet Eumic B, which orbits the roughly 20 to 40 million year old star Eumic or A Microscopy. So that's another really exciting planet that I think JWST will probably be targeting in the somewhat near future.
They did.
But
they did observations of Eumic, didn't they?
Of the disk, yes.
Of the disk, right? Okay, but not of any planets in the disk. Okay, sorry.
So I'm hoping that planet observations will be carried out. There are multiple proposals that will probably be put in. I don't know if any of them will be selected. That's always dependent on luck. That's one example, and there are a lot of other systems like that that could also be investigated. So that's a primordial atmosphere. But hydrogen and helium are very light gases, and they're very easily stripped by all of this extreme radiation from the host star. So we think that those atmospheres are lost very early. And then secondary atmospheres are produced by volcanic activity from the interior of the planet. And that is the sort of atmosphere that might allow for life as we know it to exist. Maybe not life as we don't know it, but life as we know it. And the problem with that is that there's a finite amount of volatile inventory in an Earth-sized planet. And there are models that show that for a red dwarf star system in particular, that inventory would probably be depleted sometime after around 5 billion years or so. So if you don't evolve life within about 5 billion years, you're probably not going to. There are questions, though, about secondary even generations of planets, maybe not around a red dwarf star, but you could think about a star that explodes and becomes a white dwarf and accretes a new planet. But in terms of red dwarfs, I suspect that the ones that are trillions of years old are probably going to be red and dead.
It's interesting, and I guess that goes back to what you were talking about earlier on about exovenuses maybe being a more likely outcome, that you're going to lose the hydrogen and the helium, the other lighter elements, but maybe the carbon sticks around and it's the thing that's getting pumped out and sticking around in the atmosphere of the world, I guess, depending on the surface gravity. And there just wouldn't be enough comets and things coming from outside to replenish those lighter elements.
That's my worry with the really, really old systems. Once you get well above 10 billion years, is you're going to continue to have high levels of stellar emission, X-ray and UV emission, up to the 10 billion and well beyond period. But you have a very finite amount of resources to power an atmosphere. So that balance is eventually going to tip over.
Yeah. So it's almost like even though it does get better, it never gets better enough to compensate for the damage that's being done on an ongoing basis, and
We'll
and
see.
the factors to replenish. Yeah, it is really interesting. But when you think about the potential for them to be tidally, the planets to be tidally locked to their stars, I mean, then you're only taking the radiation hit on one side, but you're still losing the atmosphere, right?
Yeah, because the atmosphere circulates. If you think about, when you turn, your heat on in a cold room, like it doesn't just get hot at the furnace. It propagates through the rest of the room as well.
So is there anything that gives you any hope for the habitability of planets around red dwarfs?
So all of the non-atmospheric detections that have been made so far have been made for some of the closest in planets to these red dwarf stars. We do not have the results yet for the ones that are further away. A good example of that would be TRAPPIST-1G. That paper will hopefully come out sometime in the somewhat soon-ish future, and that's as much as I think I'm probably allowed to say.
Mm-hmm.
But there are opportunities to look for these atmospheres on planets that are far enough away from the star till maybe an atmosphere would survive. So that gives me some hope that we haven't actually ruled out the existence of these atmospheres yet. So from an observational perspective, I think the best answer is a cautious optimism to say we don't know. For the close-in planets, I don't have much hope at all. And
Right.
that's not just true for TRAPPIST-1, that's true for most of these red dwarf star planets.
But then you have to balance. I mean, the temperature is one thing, and you can get temperature with red and infrared, but it's the flux of photons that maybe would be required to drive, say, photosynthesis, other things like that. And so, do you think there's enough sunlight for plants to grow in the places where, or life to thrive in the places where the radiation load is not so bad on the atmosphere?
It would look very different than it would on Earth, wouldn't it? There's some work that's been done on this by an amazing scholar named Ewama Shields. And so she spent quite a bit of time thinking about what photosynthesis might look like on a planet orbiting a red dwarf star. So you would see, leaves that are absorbing infrared light instead of, green light or, yellow light. So that's one thing to think about. Another factor is that, maybe there are things other than photosynthesis that we could consider. So like take the case of Europa in our own solar system. That's a very exciting place where there's a possibility that life could exist. It has all three ingredients that you would think would be necessary for life. You need to have a source of energy, you need to have the raw materials and the carbon, and then you need to have the existence of water. And Europa has all three. And that sort of environment maybe could exist around a red dwarf star. You could almost think of Jupiter as a sort of scaled down red dwarf star, and the Galilean satellites as exoplanets, really orbiting something that's very analogous to a brown dwarf, and just scale the Jupiter system up a little bit. And maybe you could expect something like a Europa situation and life existing that isn't powered by photosynthesis because it might be too far away, but maybe it's powered by just other sources of organic materials and other energy sources and deep sea thermal vents or something.
Yeah, and I have seen a couple of papers on that the amount of energy available to biology in those kinds of environments is a fraction of what you would get on a planet that is just bathing in sunlight. And
Yes.
and so you could have some kind of life like what we have huddled around the black smokers at the bottom of the ocean, but not necessarily what we sort of imagine, our European space whales, swimming past. It just would be tricky to get anything that vibrant and diverse. So it sounds right, but there isn't any kind of because every now and then someone goes, oh, actually, if a planet has a significant enough magnetosphere, it can protect itself from these flares. Do you think there's just no, are you skeptical that we're going to find some mechanism that keeps these planets protected this close to the star?
I actually have some colleagues that are working on identifying those mechanisms. One is Ekaterina Ilin, who's been working on mapping the active latitudes at which star spots are emitted. And she's been doing some amazing work showing that, the largest spots on especially the youngest stars are preferentially emitted towards the pole of the star,
Hmm.
away from the plane of the solar system. And so even though that might not protect you from the UV or X-ray radiation of the flare, it would protect you from the particle events that correlate with it, and the particle events likely do far more damage than the UV radiation ever could. So that's something that gives me a bit of hope. Another result is that we see for the sun that most flares of a certain size tend to be correlated with a coronal mass ejection that erupts. We call it an eruptive CME. And M dwarfs or red dwarfs have much stronger magnetic fields in these features than our sun usually does. And so there is a lot of evidence that eruptive CMEs might actually not be as common for a red dwarf system as for a solar type star, because the magnetic fields are so strong they essentially trap the CME, and it never actually reaches the planet, or just rather fewer CMEs reach the planet. And that's something that's also a current area of research. And Julian Alvarado Gomez at Harvard is someone who's been working a lot on those sorts of models.
What if you go below the mass of, say, a red dwarf down into like the brown dwarf range? You're still getting heat coming from. I mean, in theory, there's a habitable zone around a brown dwarf, but you're not necessarily getting the light. Does that sort of make you more hopeful again?
I don't know. I haven't actually thought much about habitable planets orbiting a brown dwarf, but I think I would go back to my Jupiter analog with that.
Yeah, that's what I was thinking.
At that point, I think you'd be looking at something more like the black smokers kind of scenario in the very low biomasses. The nice thing about brown dwarfs, though, is we think that they don't emit large stellar flares. So.
Oh, that's interesting. Okay, so they don't have the same capacity to do flares like a star.
Their flare studies all the way down to what are called L and T dwarfs. And we see a fairly high flare rate all the way up through around the L1 to L2 subtypes. And somewhere around L3, the flare rate seems to just start dropping off. I guess the magnetic fields, just don't have the kind of energy that they do at the earlier types that you see in most of these other red dwarfs or ultra cool dwarfs.
So what do you think, what lessons do you think that we can learn about all of these other stars that we're studying as we think about the history of the solar system, the evolution of the planets, and sort of how the place we find ourselves in the universe?
That's a really good question. This is something that, again, it's worth bearing in mention that in the discipline of exoplanet science is very, very young. And anything that I or anyone else says to you is very, very provisional in that regard. My favorite quote on this topic actually comes from Professor Stephen Cain in the UC system, who has done a lot of work on comparative exoplanetology and runs a very vibrant group there. And my favorite quote from him is, I think that our solar system is probably a freak of nature. If you think about what most exoplanet systems or the average exoplanet system looks like, the typical planet is going to be larger than Earth and smaller than Neptune. We don't even have one of those in our solar system. The rate of Jupiter-sized planets at Jupiter distance orbits seems to be around 10%. So that also says that there's some things that are a little bit different there. So it's probable that, maybe 3% or so of solar systems might look like ours. But I think if you're looking for the average solar system, you're probably looking at one of these M dwarf systems, or maybe a system with these sorts of super Earth or sub-Neptune mass planets. And it's just a reminder that the universe is more strange than we might expect. And until you go and you look, you never know what you're going to find.
But it is kind of amazing at this point, as we have more than 5,000 known exoplanets, thousands and thousands of more candidate planets, that we're getting to the point where we don't even, we can look at them en masse and start to make these statistical studies of how planets tend to be. And imagine going back to you 20 years ago and saying, this is what will be possible.
There were people, I've heard plenty of stories of senior researchers telling, junior researchers who are now, senior faculty members, don't do exoplanets. This is a fad. It's going to blow over. Study something else. And that's laughable in hindsight. Yeah. But at the time, it was a real worry. But in terms
that they
of
would never crack it.
They would never crack it.
Wow.
That it was just going to sort of, fizzle out is sort of what the worry was. But, now we know that there is a planet orbiting essentially every star based on the Kepler statistics. We know that eta Earth, or the rate of Earth-sized planets orbiting sun-like stars, is probably around maybe 25% or so. There's a lot of uncertainty in that number. Different studies have gotten everything from 1% to 100%. That's actually a problem with the way the Kepler mission was designed. That's a separate issue. And then, of course, NASA TESS has been observing large numbers of planets and continues to do so with large numbers of fuel reserves and a wonderful extended mission. So I think the future is pretty bright there. I will also mention, though, that of those 5,000 planets you mentioned, there are significant detection biases in what we can observe. And so you can't go straight from the exoplanet statistics, downloaded from, say, the NASA EXO archive to the true underlying distributions of planets. That's very dependent on statistical models.
Yeah, where's our hot Jupiter? Right.
Exactly. They're easy to observe, but they're actually pretty rare.
Yeah. So what are you obsessed with right now?
Right now, I'm obsessed with trying to understand the effect of flares on the chemistry occurring in exoplanet atmospheres and observing it with JWST. Thus far, most JWST observations of planets orbiting red dwarf stars are not carried out with simultaneous observations at the sorts of wavelengths where we typically monitor solar flares from the sun. So think about what we do even here in Boulder with the Space Weather Prediction Center. We say there's going to be a giant aurora that will be visible on this night from this solar storm, and here is the flare that occurred 2 days ago on the sun that's correlated with it. I'm trying to replicate that, but for planets that orbit other stars. And what you need for that are simultaneous observations in the X-ray, and preferentially also in the UV, at the same time that you're carrying out your atmosphere observations so that you can both see a flare occur from the star and then on the timescales of hours to days later, see the effect of that flare on the planetary atmosphere. This is extremely difficult to do, and the chance of success is low. But if you don't try, the chance is zero.
So you would need, you would be watching a star with something like, I don't know, Swift or something. You would be looking for that detection of X-rays coming from that flare, that it's a known flare star. And then you know roughly when the transit is going to happen so that you could make the observations of the atmosphere, and you're looking for the delay. And then you're like, quick, we saw a flare. Can I borrow JWST for a couple of hours, please? So that I can see the effect on the atmosphere? That's the plan.
It's a little harder than that.
Okay, sorry.
So JWST loves to say no. 90% of the time, they just say no. It doesn't matter how exciting the science is. Their default answer is no. It's like you go to your parent, ask, can I please have and before you even finish the question, just no. The way to do this is to go through the standard proposal review cycle and do what's called a joint program, where you specifically ask for time to be triggered on multiple observatories. So, for example, you can do a simultaneous HST and JWST program. You could do a simultaneous Chandra and JWST program. Swift is actually not an option right now. You can ask for what's called director's discretionary time to try to sort of tack on to existing programs. But coordinating multiple observatories for this sort of science is not something that I think NASA had particularly thought about. And so the logistics to do it are not quite there. So right now, what I and other researchers are doing is demonstrating the need for those logistics so that in the future, they'll be more open to doing that kind of science rather than just killing it in the review cycle because it's something no one's done before.
And you're not just asking for one parent. You're going to get two parents saying no to you simultaneously, which is even trickier.
Yeah, that's called double jeopardy. So anytime you want to coordinate multiple observatories, you have to usually go through two different time allocation committees, both of which will say, well, the other telescope hasn't agreed, and so therefore we should down select the proposal for our telescope too.
Right. Or propose a new mission that does this. That, a test.
Funny you should mention that.
Oh yeah? Is this a plan?
Yes. So there are multiple missions that are doing that sort of thing. One of the ones that I'm involved with is a NASA Small Explorer mission concept called SBEX, which would have simultaneous UV and optical observations of planets orbiting very, very young stars in nearby open clusters. That is PI'd by my former postdoctoral supervisor, Meredith McGregor, who just took a faculty position at Johns Hopkins and is putting in this proposal through through JPL. She's a faculty member at Hopkins, but is putting the proposal in through JPL. And we have not yet gotten to the gate review stage. I'm working as the FLIR's science lead on that particular mission as we're trying to develop that concept. And I think you can see the motivation of like why I would be interested in that based on this conversation. But there are also, exoplanet science cases and accretion science cases and disk things that could be investigated.
It's interesting to me that there are these, I mean, like you've got these Swiss Army knife type telescopes like Hubble, and then you have ones that are in a more specialized wavelength like JWST, very powerful, able to see whatever they can see in this field. But a lot of really interesting discoveries come from these more specific single questions that they're trying to answer. It's a simpler technology stack, but doesn't have the wide application range. In your experience so far, do you find that one is more interesting to the astronomical community over the other? And have things changed since JWST was however many years late and how many $1 billion over budget?
Things have absolutely changed. In previous generations, you could absolutely propose for a mission that was designed to answer a single science question. That is no longer considered compelling, even for the smallest missions. So there's different classes of NASA missions, like you've got the Discovery missions, and you've got the mid-X or mid-Explore missions, and a good example of one of those would be Kepler. And then you have the small missions, and even those have to show broader applicability now. So the funding has just gotten tighter and tighter, and depending on what happens with Mars sample returns, small mission calls, like for example, with the Small Explorer, may actually get delayed another year, or maybe the sample return will get canceled. But NASA has very finite resources, and they continue to be stretched further and further.
Yeah, that's what we were reporting on for a decade. Was not, boy, isn't it going to be exciting when JWST finally comes out? We were talking about the things that were getting cut, delayed, right? And everyone's really excited about the outcome of the science, and we're getting it now. And we're all just, it's nonstop. It's a fire hose of amazing discoveries. And yet I sort of think about all of the projects that we reported on that got delayed. And even now we're still sort of experiencing these delays for this process.
Absolutely.
And we're about to go through this again with sample return. And I think there's a lot less appetite from funding agencies to sort of let these things go over budget.
Absolutely. It's a major concern. Like one thing we're living in right now is this golden age of multi-wavelength astronomy that's been made possible by Chandra and the X-ray, and Hubble and the UV and the optical, and into even the beginning of the near IR, and JWST and the near IR and the mid IR. And maybe there will be other facilities that will allow us to probe into the far IR someday. And so we call these the great observatories, right? And there's this idea of what's next? What are the next great observatories? And this is something that is Grant Tremblay's hobby horse of we need to be prioritizing building those now, because if we don't start the technology development now, we're going to have several decades with nothing once the current facilities are retired. And that would be a travesty.
Yeah, and I know Grant is really excited about like an X-ray, next generation X-ray telescope, among other things. But that's what we talked about last. If people want to sort of keep track of your work, what's the best place to do that?
There's several avenues. One is my website, which is wardhowardastronomer.com. I can send you a link to that if you'd like. Another
put it in the show notes.
Would be, the archive. You can, search by individual researchers on archive and, just see what is recent. And that's probably going to always be the most up to date. And then a similar facility is the NASA Astrophysics Data Service, or ADS. You can also search by researcher on that, or by ORCID ID. So thank you for asking.
That's the best social media is archive, I think, to follow these days. Awesome. Well, again, thank you so much, and good luck with both untangling this problem and also getting your future space telescope launched.
Well, thank you.
All right.
It was good to meet you, Fraser.
I hope you enjoyed this interview. I'm going to talk more about my thoughts and reflections on the conversation that I just had. But first, I'd like to thank our patrons. Thanks to David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiblin, Jay Dennis, David Giltoned, Modso George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verboff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I think the most important thing to keep in mind as we learn more and more about exoplanets is to just be patient. And I know that we want to know, are there other Earth-sized planets orbiting around sun-like stars out there in the universe, in the habitable zone? And like the answer is almost certainly yes, and it's just inevitable that we're going to find them. And then the next question is, but is there life there? And that is such a profound question that it's going to take us a while to get a satisfying answer. There's no easy solution. When we think about how difficult it is to observe the atmospheres of Venus and Mars, and those planets are really close to us, just imagine how much more difficult it's going to be to observe planets orbiting other stars with telescopes and techniques that haven't even been developed yet. So these answers aren't going to come quickly, but enjoy the journey that we will sort of update you with every new development, every new discovery, each iteration, and over time we'll build up this more comprehensive understanding of our place in the universe and whether we are or not alone out there. And I find just every day exciting as we learn more about this stuff, and I'm okay to wait a few decades to find the answer. Now, if you want to learn more about exoplanets, I've got two really fascinating conversations that I did pretty recently that I think you might enjoy. One is with Dr. Jessie Christensen. She is the head of the sort of main repository of exoplanet information and has started a new podcast and is just a walking database of really cool, interesting exoplanets. If you want to hear all of the sort of the latest, most fascinating discoveries, definitely check out that interview with Jessie Christensen. And my other interview is with Dr. Ben Hord, and we talk about the challenges of observing exoplanets, even with JWST, trying to look into their atmospheres, figure out what they are, and figure out the priorities. Which planets are the ones that we should look at first, and which are the ones that maybe we should wait until we've got more information before we spend valuable JWST time on doing follow-up observations. So both are really interesting conversations, and I hope you will enjoy them too. All right, we'll see you next time.